So this is from our book. If I could spell book. This is section 9.2, number 20. We're supposed to find the area inside the shaded curve. Our function is r equals theta, and r equals theta is going from 0 to pi over 4. All right. So let's see. There's my pens. So you do your best to sketch that sucker. So just a note, over here, that would be pi from the origin. Over here, we're 2 pi from the origin, 3 pi from the origin, and 4 pi from the origin over there as we spin around. So there's 1 pi, 2 pi, 3 pi, 4 pi. Okay, so let's see. I think, we can't just integrate from 0 to 4 pi, because I think that will give us overlapping areas. Let's think about that for a sec. Let's bring out some red. So if we integrate from 0 to pi, we'll get that little inner part. And then from pi to 2 pi gives us that chunk right there, which is white. We don't want that. We only want the yellow. If we integrate from 2 pi to 3 pi, that gives us more than what we want, because it's going to give us, because remember what's going to happen, let's see, that got messy. We're going to have to do multiple integrals, yeah, to pull this off. I'm pretty sure. I can't see a way not to. I'm going to blow this sucker up. Let's make a copy of it and paste it. I missed. Oh, come on, blow up, please. My pen is not behaving. There we go. Okay, that's what I want, a bigger version of you. Yeah, so for example, right here is when theta is 2 pi. And as we integrate out, for example, over here somewhere, this is 3 pi over there. Over here, we're going to actually get this whole wedge, which includes some of the white area inside that we don't want. So we're going to have to do this in pieces. So I think what we can do is we can just break it apart like that and do the top part in 2 integrals and the bottom part in 2 integrals. So I think for this top part here, if we take the integral as theta goes from 2 pi to 3 pi, that'll give us a little bit more than what we want. So then we'll have to subtract that chunk right there out. And what are the bounds on that chunk right there, do you think? 0 to pi, yeah, so we'll have to subtract the integral from 0 to pi. Then we're going to have the same antiderivative the whole time. It's just going to be a bunch of additions and subtractions to make it happen. So our integrand is going to be 1/2. Oops, I should put it back to blue. So our integrand is 1/2 our radius function, which would be theta squared d theta. Yeah, so then from that, we'll have to subtract off the integral from 0 to pi. All right, so I guess I need a new page to write this out on. So integral from 2 pi to 3 pi of 1/2 theta squared minus the integral from 0 to pi of 1/2 theta squared d theta. That gives us the top half. The bottom half, let's think about that one now. For the bottom half, we'll have the integral from, remember that's 3 pi right there. Ooh, my pen is not tracking right. Let me try this again. Okay, so that's 3 pi there, that's 4 pi. That's better. So that will give us more than what we want because that'll include this region right here. So we'll have to subtract out that chunk, which is from pi to 2 pi. Oh, which is a continuation of the integral we just subtracted right here, right? Yeah, so it looks like we can integrate fully from 2 pi all the way to 4 pi, and then subtract out the inner part of the spiral, which is from 0 to 2 pi. See what I'm saying there? Yeah, I think that all fits together now. Okay, let's do it. So modifying what we have here, I think now we can go from 2 pi all the way up to 4 pi, and then subtract off from 0 to 2 pi. That's interesting. Let's see how this works out. So there is a 1/2 everywhere, right? So we can just pull out the 1/2, and then we'll have two chunks. We'll have theta cubed over 3 is our antiderivative from 2 pi to 4 pi minus, and let's put the 1/2 around the whole thing, that same theta cubed over 3 from 0 to 2 pi. All right, so 1/2 times, let's change to curly bracket, and I have 4 pi cubed minus 2 pi cubed over 3, and then minus, and I'm going to distribute the negative as I do this. Oh, there's not much to distribute, is there? There's going to be minus the 2 pi cubed over 3, and then it'll be minus a minus 0 or plus 0, which doesn't really matter, does it? And cleaning that up a little bit, what do we get? This should clean up pretty nicely because we have a common denominator. So new page, we have 1/2 times, let's see, 4 cubed. 4 times 4 is 16 times 4 is 64, is that right? 64 pi cubed over 3 minus, and then we have 2 of those 2 pi cubes. 2 cubed is 8, times 2 again is 16. So we're going to have minus 16 pi cubed over 3. I did that right. 64 minus 16 on a good day is 48. And we want half of 48, which is 24. And 3 goes into 24 8 times. So it looks like that section is 8 pi cubed for the area. So I guess I should label it square units. Oops, my pen is misbehaving again. Oh no, cut it out. Square units. And unfortunately, they have answers to the odd problems, not the even ones. So the only thing I wanted to do to double check myself here is I was kind of wondering with the addition and subtraction stuff, if Did anybody kind of wonder, is that the same thing as integrating from 0 to 4 pi? Or is it different? At first I thought, oh, maybe this is the same as integrating from 0 to 4 pi. Am I making more work for myself? But here's when I realized it wasn't. If I had added these two together, then that would be going from 0 to 4 pi, because I took the inner part, added to the outer part. Okay. Let's see. Am I convinced this is correct? I guess we have to look back at the picture. So I think our math is correct. The question is our setup correct? So I'm just going to replay with the picture just to double check that, because I had a rough weekend and I could be totally screwing this up. So Control C, new page, Control V, and I'm going to switch pens because my big pen is not behaving well. All right, so let's see. Labeling some stuff here. Right here is definitely pi out from the center, because we swept out once. And so we come around, this is definitely 2 pi there, and this is definitely 3 pi there. If we were to integrate from 0 to pi, that would generate this region right here for sure. Now we don't want that. If we were to integrate from 2 pi to 3 pi, that would put out radii like this one right here, which means it would include that inner area, right? So as we calculate area, as this thing sweeps around, it recounts the inner area over and over again as it spins. You get what I'm saying there? Right? Because the way our area works is all our function does is say, hey, there's a point this far away from the pole. And over here, there's another point that far away. And our polar calculus finds the entire sector area. So which means we are then double counting in here when we do that, if we kept spinning. So if we want just the yellow stuff, then yeah, we should integrate from 2 pi to 3 pi and then take away from 0 to pi. Yeah, I'm pretty sure we did this right. What do you guys think? More convinced, less convinced? Because we did from 2 pi to 3 pi, and then we subtracted that area in there, which left us just the yellow stuff. Yeah, we're good. All right, cool. All right, we're going to move on to a new topic. That was fun and exciting. The other exciting thing we did last week, remember, was to do arc length. And the thing about arc length is, for many problems, because you have that square root, there's just no fundamental antiderivative, and you got to resort to some kind of numerical calculation system like the integral calculator or Wolfram alpha or something else. And that's just the reality of that kind of calculus. So the new stuff we're going to be doing now is stuff you've done before, but with a new name. We're going to do what's called parametric equations. And sometimes this is covered in a high school algebra class. Sometimes it's covered in a trigonometry class. It just kind of depends. Does this ring a bell, parametric equations, with anybody? Rings a bell with you, but not you. Not ringing a bell, not ringing a bell. Okay, so a parameter is just a value that other variables depend on. Okay, so that's all a parameter is. So for example, if I want to convert from feet to inches, say, I know there's 12 inches a foot. That 12 is a parameter that connects the variable, some inch measurement, to some foot measurement. Now, sometimes parameters are static, okay? In which case we call them constants. But other times parameters are dynamic. Okay, so for example, here's one that you should be thoroughly familiar with. Remember the unit circle, which we deal with all the time in this class, and you dealt with it a lot in trigonometry. So we have this circle of radius 1. And in your algebra class, you learned that, hey, if there's some angle right here, and we call that angle theta, and there's some point here, xy, we know that we can say x is equal to the cosine of that angle, and y is equal to the sine of that angle, right? So in this case, theta is a parameter that helps us find what x and y are on the unit circle. And when we make equations from parameters, we get what are called parametric equations, equations that are based on some other variable. That variable could be an angle, it could be time, it could be something else. So this is, so what we're going to play with now, we're going to, parametric equations mean we're going to have systems of equations. And those systems are going to be x and y values that are based on some other value, okay? So just for fun, Desmos does a great job with parametric equations. Sometimes I'll use theta as a parameter, sometimes I'll use t. In Desmos, come on, where are you? There we go. Desmos requires, if you're going to use parametric equations, you use t, and use theta as a point for x and y. So for example, if I go to Desmos right now, and I say, parentheses, let's delete this stuff, parentheses, cosine of t, maybe t could be theta, t could be time. Ask me if I want a slider. I'm going to ignore that for now. And then I say, okay, then I also want y to be sine of t. So here I'm building what I had a minute ago. X equals cosine of t, y equals sine of t as a point. It says, oh, do you want the unit circle then? And here it's saying theta goes from 0 to 1. For the unit circle, how far should I let t go to? 2 pi. So I say 2 pi and it builds the whole thing. It's kind of cool. If I back it off and I say, hey, only go up to like 5, it stops there. If I say go up to 6, not quite 2 pi, and I could have it keep going if I wanted to. And you have to enter t. You have to enter it as t. Yeah, yeah. And then I can make it kind of animate this, and I got to trick it to do that. So what I do is I make a different variable. Like let's say my variable is going to be a for like alpha. And if I hit enter, oh, it didn't make a slider. How do I get it to make a slider? A equals 1. Ah, there we go. Okay, so then I'm going to say a is going to go from 0 up to 2 pi. We're not going to worry about the steps for now. And then over here, I'm going to tweak this just for fun. And I'm just going to throw in a there too. And so now I can kind of animate this thing. I can say, please draw out my circle for me. And so it's just letting I just changed the parameter from a to t with a little tiny trick. And so that's drawing out the unit circle. Okay, so parametric equations are just, usually we use the xy coordinate, but it could be polar. We're not going to mix polar and parametric. That we're not ready for that yet. That's too mind-blowing. But what we're going to do is we're going to stick with the rectangular coordinates, and we're just going to throw in some other parameter. Okay, and here we've developed the unit circle. Now, oops, where's my notes? Here we go. The traditional definition in trigonometry is to let x equal the cosine and y equals the sine, because of the way we say sine is the opposite angle over hypotenuse, cosine is adjacent over hypotenuse. What happens if we mix that up? Like, what if we make a new set of parametric equations and somebody says, hey, I want x to be sine for a change. Tired of making x equal to cosine. What would happen here if we switch the roles of x and y? So let's try that in GeoGebra and see what happens. GeoGebra, where'd you go? Over here. So I'm just going to switch these. I'm going to make that sin. Ooh, look at that. If I let them both be sine, I get a straight line. And it just grows and grows and shrinks. Interesting. Crazy. All right, pause that sucker. Oh, I should put a point on there to track it too. Anyway, way too much fun. So this is like your own little math video game. If I switch sine and cosine, check it out. It reverses the direction and starts it at a new place. Right? So we're just switching the x-axis and the y-axis is all we did there. Okay. There's other ways we can switch things. So there's lots of play we can have here. I'm going to put it back to the traditional. let's see, what did I have first? Cosine and sine. And instead, I'm going to see what happens if I make both of them negative. And so then I'm just saying, hey, go backwards that way. Other things I can do is I can play with the speed of the parameterization. Okay, so maybe t is, or a is time in seconds. What would happen if I threw in, let's get rid of the negative, make it go in the positive direction. What if I threw a 2 times in there? It graphs faster and longer. So what's happening is, as I get to about pi, it completes the circle, and then it keeps going. So it's going to trace the circle twice in this case. So the trick about parameterizations are we have to keep track of more than one variable now. We have x to keep track of, y to keep track of, but we also have to think of what's the domain of our parameter. Okay. And so you say, okay, well, who the hell cares about parametric equations? Well, it's a good question. I'm glad you asked. Parametric equations come up in a lot of different areas. So, for example, one is in physical design of things with, say, machinery. If I want a machine to trace out some pattern, how do I tell the machine to trace out that pattern? Okay. How do I tell it to do that? Well, one way to do it is to give it a pair of parametric equations. As time goes by, x does this and y does that. And so the computer can learn to trace a curve through space using parametric equations. If we needed 3 dimensions in there, we just throw a z in there, and then we can have the machine go in 3 space and move around and do whatever we tell it to do. Right? We can control its movement through a parameter, which is kind of neat. And so that's the way a lot of CAD stuff gets made 3-dimensionally, like laser printers and whatnot. We tell the thing how to move with another parameter, which is kind of neat. Other things that are related to this. If you think about it, in a lot of the math books you looked at in algebra classes, there was always this ball is dropped from a roof, or somebody throws this thing straight up in the air, right? And we always get this parabola shape when we do that. But we're not looking at the object going through space. We're watching the object going up and down. We're just plotting its height, okay? So it turns out parameters are involved if I watch something move through space. So I'm going to do a little experiment here. And those of you on the internet, I'm sorry. Oh, maybe the camera will help do it. We'll try the camera. So what I'm going to do is I'm going to stand still, and I'm going to throw a pen. So here's my pen. And I'm going to launch that pen, and it's going to fly through the air, and it's going to hit the ground, right? Boom. And so the question is, what kind of path does it trace through space? Okay. Well, some things we need to know to do this problem are, one, that gravity is in a force that affects acceleration. And have you guys all had physics a little bit? Okay. And acceleration is the rate of change of velocity. And so we experimented, and on the surface of the Earth, does anybody remember about what acceleration, the force of acceleration, the force of gravity gives us for acceleration near the surface of the Earth? It's about 9.8 meters per second per second. 9.8 meters per second per second. And then we know through calculus that if we integrate that, then we get velocity, and that means velocity is going to be 9.88, there we go, meters per second times time plus some initial velocity. And then if we integrate that again, because velocity is change in position over time, then we get kind of a position out of that where we're going to get 1/2 of 9.8 meters per second times t squared plus the initial velocity times t plus some initial position. Okay. Now that's only vertical movement though. That doesn't take into account horizontal movements. Does gravity have anything to do with something moving horizontally? The answer is no, it does not. Air resistance might, but not gravity. So what I have here is that position right there is really just the vertical position of the object. Okay, so maybe I'll put a piece of V there, P vertical. Maybe I'll write vert to not confuse it with velocity. That's only the vertical. What's happening horizontally? Well, the other thing to take into account here is when I throw this pen at some angle, so this is my horizontal here, there's the angle I throw it at, we can break that velocity I give it up into two components. There's the vertical component of the velocity and there's the horizontal component of the velocity. Okay. So let's take a look, see if my camera will show some of what I want to see. Hello, camera. How much do you show? Not very much here. So I've got my pen here. Ooh, bright light. Ah, I'm going into the light. And then I'm going to throw the pen, and the screen didn't really catch it. Bummer. All right, so let's see. I was here. That's about 1 meter. It went a little over 2 meters. Do you guys see how high it went? No? Okay, let's do this again. Ready? So watch. Guess about how high it goes. So look at the board. And I'm going to try to throw it at about 45 degrees. And I've got a little accelerometer built into my arm here. And so I programmed the accelerometer to throw it at about 5 meters per second. So let's see if I get this right. Okay. Okay. So 1, 2, 3. It went a little over 3 meters, maybe 4 meters horizontally. Anybody see how high it went? This high or higher? Did it go higher than the board? No? So the board, so that's about, let's see. This is about 2 meters right here, I think, right here. So maybe just a hair over 2 meters, maybe? Okay, so I'm going to program into Desmos what just happened. So just a note, I'm guessing that the velocity I threw it at was about 5 meters per second. Is when oops, I forgot to switch back to my screen. Okay, so I'm guessing at about 5 meters per second. Now there's a vertical component to that and a horizontal component. Well, the vertical component is just the sine of the angle times that, and the horizontal is the cosine times that. So vertically, I'm going to have the sine, and I attempted to go at pi over 4, 45 degrees, pi over 4, sorry, times 5. And horizontally, I guess I don't need any extra symbols there. Horizontally, I was attempting same thing, so that would just be cosine, oh shoot, pi over 4 times 5. Now, sine of pi over 4, cosine of pi over 4, those are both square root of 2 over 2 or 1 over the square root of 2. So I could say then vertically it should be about 5 over square root of 2, and horizontally it's about 5 over square root of 2, or roughly like 70%-ish of 5, which should be like 3.5 feet per second, maybe. Okay, and so really what's happening is it's moving horizontally while it's going vertical. Vertically, it had that initial thrust, but gravity's saying take it, it's pulling that away from it, right? So it's dropping. And so horizontally, it's moving the same speed, about 3.5 meters per second, when it leaves my hand and when it hits the ground. It's just gravity finally makes it hit the ground, and that's what stops it. Okay. So as far as so my v sub 0 is this guy up here, and horizontally, since there's no gravity, the position is just rate times time. My rate is 5 over square root of 2 times time. Okay, so I have a parameterization that should track my pen through a plane. So let's do this. Okay, so let's see. Let's get a new Desmos screen up. And whenever we're doing parametric, we do it as a point in Desmos. And then horizontally, I just have 5 over the square root of 2 times t. And then vertically, I have gravity. And gravity, oh, I forgot the negative. Gravity has a negative. It's pulling down. So that's negative 1/2 times the 9.8 times the time squared plus the initial velocity I gave it, which I'm estimating to be 5 over square root of 2 times t. So that's distance equals rate times time, right? Ignoring gravity for a sec. And then I threw it at about from my waist. Does that sound about right? My waist is about 1 meter off the ground. So I'm going to estimate that the initial height was about 1. And it doesn't like something I typed. Maybe I need a times here. Times time. Ooh, shit. That was interesting. Undo. Ah. And then times. Still doesn't like something I typed. What doesn't it like? What are the times there? Okay, what don't you like? You like T earlier. Oh, where'd the A come from? Do I need a times there too? Ah, I wanted the times there. Okay, so Desmo's expecting me to multiply. Yeah, we need to zoom in on this sucker. Make that. Can I make you go away? There you go. Oh, get back here. All right, so according to this, all right, so I must have either thrown it at a steeper angle or faster than 5 meters per second, because notice it didn't go as high as we saw it go. I was estimating it went somewhere between 3 and 4 meters when I pasted out, so that wasn't too bad. So what do you think? Change the angle or change the initial speed? I mean, I programmed my accelerometer in my arm, but I forgot to program the angle. So I'm thinking I screwed up the angle. Is that what you're thinking? Yeah, he noticed I didn't program the angle in. All right, so what I'm going to do is I'm going to get rid of the square root of 2 in the bottom, and I'm just going to multiply by, horizontally, it would be the cosine of the angle, right? So what angle is it? Do a little times in case it gets screwy on me. So pi over 4, maybe I threw it steeper than that. Okay, so pi over 3 is probably too steep, but let's try it. All right, and then I have to change this one too, because they both have to match. So this one is what? Sine of the angle we threw it at. And let's put a pi over 3 there. Pi over 3. And, oh, we should have timed it too. That's 1 second. It didn't quite hit the ground after 1 second there. But notice it did get closer to 2 meters high, but it definitely went more than 3 meters, right? So probably I don't have the angle or the speed right. And, you know, pi is about 3, right? It's a little over. So that means this angle right here is a little over 1. So maybe it was more like an angle of 1 radian. And maybe I threw it at 6 meters per second. Maybe my accelerometer is a little off and I got to get it checked out. Oh, but then it's going too far there. And too high. Yeah, so maybe it's 5.5. Yeah, oops. But this is kind of cool. This is what parameterizations are all about. You have something. Oh yeah, that looks pretty good right there. Maybe it's 5.5. And then 1.2, okay. And it's somewhere between 1 and 1.2 seconds, 1.1 second maybe I hit the ground. So we've parameterizations, they're kind of fun things. There's all kinds of things we can take and program in. Sometimes it's an angle, often it's time. Time is a parameter we can't stop. Right? Everything depends on time. Okay. So it's just another variable that other variables depend on. Now sometimes we like to get rid of the parameter because that's a lot of stuff right there. Okay, so let's just do a simplification of this problem and get rid of the parameter. So let's suppose in a simplified version, oops, I'm going to dumb this down a little bit. It will work. So suppose we have that x is equal to, let's call it 3t, and y is equal to, let's see, 9.8, that's pretty close to 10, half of 10 is 5, so let's say it's -5 t squared plus 3t. Let's say it left at perfect 45-degree angle, and then plus 1. So suppose this was my parameterization right there. Sometimes we want the parameterization to just be a traditional rectangular function, which means we have to find a way to get rid of t. Okay, well that's not too bad because the top equation gives us the perfect opportunity to do so. Because according to the top equation, t is equal to x over 3. So then I can come back over here and I can say, oh yeah, all right. So that means y must be equal to -5 parentheses, replace t with x over 3 squared, plus 3 times x over 3, plus 1. And then we could clean that up a little bit more. So what do we get there? -5/9 x squared plus x plus 1. And if we throw something at a 45-degree angle, the initial vertical speed and the horizontal speed will always match, and they'll divide out. If it's not a 45-degree angle, they will not divide out, okay? Because we'll have slightly different numbers here and there. But we can, now it's a rectangular function, and so we could have done the same thing with our parameterization for the real physical problem. It'd be a little messier in terms of the numbers, but then we wouldn't have t involved anymore, okay? So the question is, well, this certainly makes things simpler, right? And I can see the path the object makes through space based on this, but what I lose track of is what time did we reach a certain position? So that's the nice thing about the parameterization. The parameterization says, hey, here's where you are x, here's where you are y, and we know what time it happened at. So the parameter gives us more information that could be very useful, okay? Sometimes we get rid of it because it makes life simpler. Other times we leave it in because we need that information. Okay. Sometimes there's a parametric equation where you can't solve for t and you're stuck with it in parametric form, that there is no traditional rectangular function to represent it. Okay. And it just kind of depends. All right, let's do another problem. Other things about parameters is we have control over where to start the parameter, where to stop the parameter, and how fast the parameter gets to move, okay, by using multiplying factors and shifts. So let's play around with that idea. So let's suppose we have 2 points in space. Ooh, that's horrible. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's x and here's y. And suppose I have the point 1, 2, and I have the point 5, 4. And so what I want to do is I want to make a parameterization to get me from this point here to that point there in that direction. And I want to start t equals 0 there and end with t equals 1 there. And so we can make a little table to help us think about this. So I have t to consider, I have x to consider, and I have y to consider. And so when t equals 0, x is going to be 5, right? And y is going to be 4. When t equals 1, x is going to end up being 1, and y is going to end up being 2. And so let's just focus on t and x for a moment. Well, all I need is to get from essentially when t is 0, x is 5, to get from 1 to 1. So couldn't I just say something like, well, there's a rate of change here. X needs to drop 4 units over that time. So couldn't I try something like x equals drop 4 units over time, starting at 5? If I consider the slope here to be a drop of 4 and a rise of 1. So we'll try this out and see what happens. Y, on the other hand, So I want to consider t and y. Over that same change in time of 1 unit, y has to drop from 4 to 2. It has to drop 2 units in 1 unit of time. So time-wise, there's a rate of change for y of a drop of 2 y units for every 1 unit of time. So negative 2 over 1 times time. But the y value has to start at 4. So I think that will work right there. So I'm going to test that parameterization out on the page here and then in GeoGebra. So just to double check, if I wanted to calculate, okay, is this going to put me in the right spot, for example, when t equals 1/2? So if I plug in 1/2 here, half of negative 4 is negative 2 plus 5 is going to give me x equals 3. And half of negative 2 is negative 1 plus 4 gives me 3. Should I be at the point 3, 3, right in the middle there? Seems reasonable. All right, let's see if we can get Desmos to agree with us. Let's see, let's do another Desmos graph, unless we need, oh, we're almost out of time for fun with this? Man, that went by way too fast. I had another wicked cool example to show you. All right, so in Desmos, to do parametric stuff, it's a point, and you type the x function in terms of t. So what do we have? Negative 4t plus 5. And sometimes it wants you to put a multiplication symbol in. I think we'll see what happens. Oh, looks like we're okay today. Negative 2t plus 4. And that should take me from the point 5, 4 down to the point 1, 2. Okay. So that did work. Cool. And then if we wanted to, we could solve, say, this one right here for t, and we can turn it into just a traditional equation. So for example, if I subtracted 5 to the other side, I'd have x minus 5 and then divide by negative 4. That would tell me what t is. And then I could substitute that in here, and I could end up with a traditional function, y in terms of x, and clean it up, and it would give me the slope and the y-intercept and all that. I'm going to forego that. That's pretty simple. So I'm just going to give you a preview of what I'm going to do next class. So I'm a little behind schedule right now, which is totally fine. There is a really cool curve called a cycloid. There's another cool one called an epicycloid. Has anyone ever played with a toy called spirograph, where you have gears within gears, and you put your pencil on the gear and you trace out these crazy curves? So spirograph. I didn't spell that right, did I? Oh yeah, maybe. All right, so I'm going to show some cute images. Yeah, so you have these gears, and you place one gear inside of another or outside of the other, and the gears have little holes in them for a pencil, and you just kind of trace and move in circles, and you get all these crazy patterns. Some of these are called epicycloids. An epicycloid is what you get when you watch a point in or on one circle move as it rolls around another circle. A simpler version of that is what's called a cycloid. A cycloid is what happens with, if you ever watched like a bicycle moving down the road and it's got a reflector, and you watch the reflector move around, a cycloid is the pattern a reflector makes as it's moving down the road. So here's I made a little animation in Desmos to demonstrate that. Let's see, how do I get to it? Up here, cycloid parameterization. Yep, open graph. All right, so here, let me blow it up a little bit. Let's see, how do I do that? I can just zoom in, right? Yeah. So I have this circle here, and the circle is going to roll across this flat plane, and we're going to watch the path this point makes as the circle rolls. Okay, so it rolls out and it creates this new shape. This new shape is called a cycloid. And it turns out what we can do is, if I bring it back to the origin, if we mark the center of this circle and draw a radius from that center to this point, and we watch how that radial arm moves, it's going to be tracing out an angle. And if we track that angle, the angle lets us track the point. So we can make a parameterization of this curve. Okay, so what? Who cares about a cycloid? So what? It's a point on a bicycle tire rolling down the street. I don't really care. Well, it turns out it solves some really cool physical problems, and the physical problems that it solves are really amazing. It was posed, I think, in the mid 1700s. Suppose you have some point A here and some other point B down there, and you want to make a path from point A to B, so that when you put a ball at point A and you let it roll, ignoring friction, just gravity rolling down the slope, what curve should you have that it gets from A to B the quickest, right? And guess what the first thing people came up with? First people saying, well, a straight line is the quickest way from point A to point B. And that's only if you're moving at a constant velocity. But we have gravity going on here, which makes velocity not constant anymore. Okay, so then the question is, what is it? Is it part of a parabola? Is it part of a circle? Is it part of a hyperbola? Is it part of, I mean, what is it? And it turns out somebody showed hundreds of years ago that it was this cycloid curve that lets you roll the fastest from point A to point B. Okay, and that problem was called the brachistochrone problem. It's a tough word. There was another problem that was posed around the same time, is what curve could you make so that it doesn't matter what the starting point is, A or C or D, it'll take the same amount of time to get to point B. Doesn't matter whether you start at point A, so if it took 1 second to get from A to B, it would still take 1 second to get from C to B or D to B. What curve makes that happen, if any? Guess what curve makes that happen? The cycloid, again, makes that happen. When you turn it upside down, you got to flip it, obviously. Isn't that amazing? Crazy stuff. And so I built a cycloid once, and it's at my house. If you ever want to stop, see a real cycloid, I have one at home. I can't bring it in because it's actually the frame of my door, my front door. So you have to just come look at my front door and say, oh, okay, that's a cycloid. But anyway, so we're going to build a cycloid in the next class. So I'll show you how to come up with the equation here, how to derive that equation right there for a cycloid. And it's not a circle, it's not an ellipse, it's just some brand new curve that we didn't know before, which is pretty wicked cool.